Okay, I'm just going to go over the CAST algorithm quickly for better clarification. Because I made some mistakes on the sheet, so I don't want you to be completely confused. As the book says, the CAST algorithm is, it offers some heuristics to help increase the speed than the previous algorithm, the PCC. So it doesn't have a performance guarantee, but it still performs well for its function. And it guarantees that your clusters will not have any gene or vertex in it that is outside of the threshold or above the threshold, but it does not guarantee that the distance within that cluster would be better than a distance within another clustering. So, meaning maybe this is the best clustering, but the CAST algorithm causes you to have something different that's still acceptable. So that may be the one drawback, or one of the drawbacks of it. But let's go through this. I put the grid here, but it's on the CAST sheet, so you can look there. The first thing you can do is create the distance graph based on your distance matrix. And the threshold is 37. So the distance between a gene and a cluster should be 37. I'm making it less than or equal to 37. So the distance between the gene and the cluster should be less than or equal to 37 for this scenario. And initially, when we're building the distance graph, we really don't have a cluster, so you can consider that each gene is its own cluster, in which case you just want the edges between each gene to be less than 37. And I missed one in my original sample, but if you look at gene 1, it has an edge between G1 and G2, G1 and G4, G1 and G5, G1 and G6, because they are all less than a distance of less than or equal to 37. And then the next one, G2, has a distance between G1 and G2 of less than 37, G1 and G2 and G4, and G2 and G5, and then G3, I only see one here, G3 and G5, and G4, we have G1, we already have that, G2, yeah. G5 is G1, G2, G3, yeah, we already have that, and G6 is G1, just G1. So this is our initial distance graph based on our distance matrix. And if you look at the first step of the CAST algorithm, it says to set your S. So S is just your vertices. So I'm just putting my genes here. And then our partitions, P, is currently an empty set. We don't have any partitions. And then while we still have genes in this set, we need to perform this loop. So initially, the vertex of maximal degree in the distance graph, G. So we're going to choose a vertex to start with And we choose the one with the maximal degree. Degree, number of edges in and out. So we have a degree of 4 off G1, only 3 off G here, 2, 1, 3. So G1 is our gene with the maximal degree. So V is G1. And then we just add V to our initial cluster. So G1 is our initial cluster. So now that we have our initial cluster, we can go ahead and see if we should start adding close genes or removing distant genes from our cluster. And if you look at the bottom of 353, it explains that the word close and distant are not general uses of these words. They have specific attributes about them. So a gene is close to a cluster if the distance between the gene, we'll say gene I, and that cluster is less than, and I'm saying less than or equal to. The book is just using less than. Actually, let's change this. We'll make this less than 38 just to be consistent. Less than 38, okay. So less than our threshold. So it's close to the cluster. Gene I is close to the cluster if the distance is less than the threshold. If not, then it's distant from the cluster. So close is a specific meaning and distant is a specific meaning. So we'll keep that in mind. So for our first, we have a cluster which only has one element in it. So this is really easy. We want to see if there are any genes that are close to G1, the cluster G1. So if we go to, so we're looking for what's close to G1. G2 is close to G1. G4 is close to G1, G5 is close to G1, and G6 is close to G1. G6 is the closest, so that would probably be, as the algorithm states, our best choice. So we can go ahead, and since we see G1 is our closest, we can go ahead and add that to our cluster. G6. Okay. So now we have a cluster that has two elements in it, and if we want to see if we know that G1 and G6 are close to each other, so we don't have to check to see if they're distant from each other. But now we want to see what genes are going to be close to this cluster. Genes are, so it's all the ones that are in S that are not part of C. So now we have G1 and G6 is our cluster. G1 and G6 are our clusters. And we want to know if there's any genes that are close to that cluster. So G1 is in our cluster. So we could check to see if G1 is distant from G6, if it's in it, since it's in it. But we already know that that's a distance of 10, so we know it's not distant. G2, is G2 close to G1 and G6? Well, let's see. G1, G2 has a distance of 31. And G2, G6 has a distance of 45 divided by 2. $76 divided by 2, 3, carry the 1, 8, 38. No, that is above our threshold just by 1. So then we check G3. G3 has a distance of 58 from G1 and a distance of 78 from G6, and I don't even have to do the math because both of these are above the threshold. So if I take the average, I'm not, that's also going to be above the threshold. So I know for sure that that's not the case. So is G4 close? 27 and 96. Again, I don't have to do that math because I know that's going to be greater than 38 or 37. G5, 12 and 43. G5 is the distance of 12 from G1, 43 from G6. So possibly that might, I'm dividing it by 2 because there's 2 elements in the cluster. So let's see, that would be 56 divided by 2. I don't even have to go to the next number because the first number is 20, it's 20 something. So I know that's less than 38. So G5 is good. It's close with we'll say 28, with a score of 28. And then G6 is already inside of it, so we don't need to check if it's close. And we know it's not far because we know it's a distance of 10 within the cluster. So we do have G5 gets added to this cluster because it has a distance of 28 from the cluster, and that is less than our threshold. So we can go ahead and add G5 to the cluster.